So for this fifth one, we have to first of all prove this identity, and then we have also been asked to see whether these other two identities are true or not. They will turn out to not be true, so we will have to show that using counter examples. So let's just prove the first one first. And the procedure is usual, showing that each one of these two sets is a subset of the other. We have, say we are taking an arbitrary element in this set. This implies this ordered pair belongs to, since it's an intersection, it will belong to both the sets. And x comma y belongs to C cross D. Then again writing it elaborately, the meaning of this: x belongs to A and y belongs to B, and like that x belongs to C and y belongs to D. Note that because we have AND throughout, so we can write these simple statements, x belongs to A, y belongs to B, etc., in any order we want, keeping AND in between them. So what we do is this: x belongs to A and x belongs to C, and y belongs to B and y belongs to D. This will directly imply, first of all, this and this, they will imply respectively x belongs to A intersection C and y belongs to B intersection D. And then in the next step we have this: x comma y belongs to A intersection C cross B intersection D. The fact that this identity works is because we have AND throughout, which is not the case with this one. From this from this Cartesian product we will have AND, but because of this union we will have OR, and they will get mixed up together, and that will create problem for this identity, which ultimately we will see is not true. Okay, so now can we go back from here? Yes, we can. This directly implies this, there is no problem with that. Also this implies this. Just like we were able to write this statement from this statement, from here also we can go back and have this one, since here also we have AND throughout. So we can write the simple statements in any order or any manner we wish. And then going further back is not a problem at all. So A cross B intersection C cross D is a subset of A intersection C cross B intersection D, and the reverse inclusion is also true. Is a subset of A cross A cross B intersection C cross D. This implies that they are equal. and the proof of the first identity is over. Now we see that these two are not true. So for that we have to produce counterexamples. So we take special values of these sets. Let A be the singleton set 1, B be this set, C be this set, and D be 4. Then what about A cross B union C cross D? Let us actually calculate. A cross B has only one element, one ordered pair, because A and B both have one elements. So A cross B has only this ordered pair. Like that, C cross D also has only one ordered pair, 3, 4. So this union is just these two ordered pairs, 1, 2 and 3, 4. But what about A union C cross B union D? This is going to have more elements. If you can see ahead of time why, and then it's much better, because A union C will now have two elements, 1 and 3. B union D also has two elements, 2 and 4. So their Cartesian product will have 4 elements. So already you are getting the fact that this cannot be equal to that set, because it has 2 elements and that is going to have 4 elements. Anyway, let us calculate. So this is A union C is 1, 3 cross B union D is 2, 4, and all possible ordered pairs will be there, where the first coordinates are coming from this and the second coordinates are coming from this. So this is equal to 1, 2, and at the same time 1, 4 is also there, like that, 3, 2 and 3, 4. So we see that the first set is actually a proper subset of this, not equal to this. So it's not necessary that we have this identity. Just like that, the last one is also not true. For that, let A be this one element set, A and B are just like before. C has these two elements, 1 and 3, and let D be the empty set. Then A cross B minus C cross D. Okay, so A cross B is just like before, 1, 2. But what about C cross D? Since D is empty, so C cross D is also empty, minus the empty set. So it is A cross B itself. But what about A minus C cross B minus D? A is a proper subset of C. We don't really need properness, but still A is a proper subset of C, so A minus C is empty set. Cross B minus D. B minus D is the set B itself because D is empty. Nevertheless, ultimately the set turns out to be empty set, so they are not equal. One of them is this and one of them is this. So here also it's not necessary to have this identity. Minus C cross D is equal to A minus C cross B minus D, and there the solution ends. So now let us see the next one. So this is the sixth one. Let now also we have 4 sets, but an additional condition is given. They are non-empty. B non-empty sets show that A cross B is a subset of C cross D if and only if A is a subset of C and B is a subset of D. But there is more, and that A cross C is equal to B cross D if and only if A is equal to C and B is equal to D. So we can improve the containment relation to the equality relation. What happens if the hypothesis that ABCD are all non-empty are removed? I need some ink. Okay, so let us go through the solution. We prove the first one first. So let us first assume the easy one. namely if A is a subset of C and B is a subset of D, then A cross B is a subset of C cross D. So first assume this and this. We have to now show that A cross B is a subset of C cross D. So let x comma y be any element in A cross B, then x belongs to A and y belongs to B. Since A is a subset of C and B is a subset of D, we have x should then belong to C and y should belong to D. This implies x comma y belongs to C cross D. Hence, A cross B is a subset of C cross D. So one part has been proved. Now we prove the converse. Conversely, let this containment be true. Okay. Now we have to prove these two things. A is a subset of C and B is a subset of D. Let we have already taken let us take something else. Let Z be any element in A. Since now this is where non-emptiness of the sets will be exploited. We need non-emptiness now. Since B is non-empty, we can choose some element B belonging to B by the axiom of, by the result single choice. Then Z comma B belongs to A cross B, and so Z comma B belongs to C cross D. This is coming from our hypothesis that A cross B is a subset of C cross D. This implies Z belongs to C and B belongs to D. We don't really need B belonging to D. That part we don't need. Our main focus is on this Z belongs to C. So any element Z in A is again in C. So A is a subset of C. Thus A is a subset of C. Similarly, using the non-emptiness of A, one can show that B is a subset of D. So we have now proved both the directions. A is a subset of C and B is a subset of D if and only if A cross B is a subset of C cross D. Okay. Now the next thing we were asked to prove is this. the similar statement with containment relation or subset relation replaced with equality. So that we can prove using what we have now proved just now. Next, okay, write the arguments in a series of equivalent statements that will prove the thing. Next, A cross C is equal to B cross D if and only if A cross C is a subset of B cross D and B cross D is also a subset of A cross C. That is true. If this equality is there, then both the containment relations are true, and conversely also, if they are true, then we have equality. In fact, that's what we do every time we prove two sets are equal. Now what have we proved just now? That this is true if and only if A is a subset of B and C is a subset of D. Keep in mind that the hypothesis that all the sets are non-empty is still there. Under that hypothesis, that's why they are writing and, that this if and only if this and this. So under that same hypothesis we are having these things. So from what we have already proved, A is a subset of C and B is a subset of D, and here the exact opposite will happen. Note that because A, B, C and D are actually arbitrary sets, so it does not matter if we write B in place of A and D in place of C. After all, they are just sets, and as long as they are non-empty and satisfying the conditions in this result, the conclusion of the result will be true. So this is equivalent to B being a subset of A and D being a subset of C. And just like one exercise before, here also you see we have and, so we can rearrange the simple statements within and write like this: A is a subset of C and I think I have written something wrong. Here I will have B, sorry about that, and am I writing it correctly or have I messed the order up? A cross B and C, oh, I wrote the thing here in a wrong manner. We will have, sorry about that. Although it does not matter, but still for the sake of uniformity we have to write what is given in the, here it is okay, A is equal to C and B is equal to D. So here we will have A, B, C, D. Here we have C, D and A, B. So A, now it's okay. So C will be a subset of A and D will be a subset of B. So now A is a subset of C and C is a subset of A, and B is a subset of D and D is a subset of B. So now you can see that this is equivalent to A and C being equal, and this is equivalent to B and D being equal. So the previous statement is equivalent to A is equal to C and B is equal to D. So that's how we have this if and only if, this and this. Now lastly we have to address the question, what happens if the non-emptiness of all the sets is that restriction is not there? Then it's not necessary that these results are true. For that we take this example. Take A to be the singleton set consisting of 1, B to be empty, C is the singleton set 2, and D is 1 with its only element 3. Okay, then A cross B is empty because B is empty, and empty set is a subset of every set, so it is a subset of C cross D. We don't even need to calculate C cross D to conclude this, because empty set is a subset of every set. Okay. Now whether A is a subset of, so according to that, if that result in this case is, had been true, if it were true, then we would have A subset of C and B a subset of D. Now B is a subset of D, that is correct, because B is empty, but A is not a subset of C. Because A has 1 which is not there in C, and you can clearly see that okay, let me just write it also, and hence can we write equality here? We cannot write equality here. Oh, but we can modify the thing a little bit. Okay, we can modify this example a little bit so that equality also works. I mean, for the equality part also this turns out to be a counter example. So what we will do is, we replace this D by empty set. What will happen then? Here we don't have to think about anything. Whatever D ultimately becomes, this statement is true, these statements are true, and also not hence A cross B is equal to C cross D, because now C cross D is also empty, but A is not equal to C, because we have not changed A and C, so this continues to be true. If A is not a subset of C, then definitely A is also not equal to C. So we see that we can have A cross B as a subset of C cross D, but not having A and C equal and B and D equal, and also the subset relation, and also for that equality. I mean, both the results turn out to be false in general if we don't maintain the non-emptiness hypothesis on the sets. So here the solution ends. Okay, next we go back to functions in the next exercise. Exercise 7. Let x, y be sets let x comma y be sets, and let, we are going to define some special functions, although the notation is really cumbersome, but it shows what the functions really are. X cross y to x pi, and in sub you have this whole thing as a suffix, and this is a function from the domain x cross y to the range x. B, and there is one more. These are projection maps, if you already know what that means. Their notation and name, these things sound quite difficult and scary, but the concept is very simple. B mappings defined by, let me write like this here, pi x cross y into x comma y is defined to be equal to x, and shall I have space, pi x cross y to y, x comma y is defined to be equal to y. So basically what we are doing is this: we have two sets and we have taken their Cartesian product, and we are finding mappings from the Cartesian product to both the sets. And what do these maps do? One of them maps the any ordered pair to its first component, and another one maps that ordered pair to its second component. So this is called the projection onto the first component, and this is projection onto the second component or second set. Show that although in this exercise the word projection has not been mentioned, something else has been mentioned, not in its place but something else entirely, direct sum of two functions. Let's write the exercise down and see what these things mean. So these are two maps we have defined for two sets. Now we have to show something about them. Show that for any function functions f from z into x, z or z is another set, and g from z into y, there exists a unique function h from z into x cross y such that pi x cross y composition to x composition h is equal to f, and pi x cross y to y composition h is equal to g. Okay, and there is something else also, a sort of remark. compare this to the last part. To the last part of exercise 338. You can go back to these exercises and see what they are talking about. And to exercise 317, something else is also said. The function h is known as the direct sum of f and g, and there is a symbol. Those of you who know about who have come across this term direct sum from algebra, they would know this notation, and is denoted like this. H is the direct sum of f and g. Okay, so that is the exercise. We have defined two functions, and for given two functions, we have to prove that there exists a unique function h of this form